Okay, good day, everybody, and welcome to our webinar on flue gas analyzers for safe combustion of high hydrogen fuels, which will be presented by Tim Tallon of Amatec Process Instruments. My name is John Kearney, and I lead the product management and technical sales support teams here at Amatec PI, and I'll be serving as the moderator for today's session. We're certainly excited to share some interesting and educational information, both on the trends in global decarbonization that are really driving the use of high hydrogen fuels. And Tim's going to talk quite a bit about how flue gas measurements can benefit operators both in improving combustion safety as well as optimizing combustion control. So before I turn the presentation and lecture session over to Tim, I just want to cover a few logistic items. First of all, we are recording the session, so everyone should be on mute, but if you're not, just to minimize any background noise, please make sure you have your phone muted or your computer microphone muted. We do want the session to be very interactive, so we will have a Q&A feature that's available. If you look on the top sort of right-hand side of your screen in the Microsoft Teams window, you'll see a question mark with Q&A designated there. You can click on that, and the Q&A box will appear on the right-hand side of your screen, and you can feel free to type any questions or comments in there, and I'll have Tim either address those questions during the session, or we'll contact you via email after the session. As I mentioned, the session is being recorded, and we will make it available on the Amatec Process YouTube page in the next day or so. And that link I'm going to post here in the chat window in a moment. Just for those who aren't part of Amatec PI, this webinar is sponsored by Amatec Process Instruments. We are a worldwide manufacturer of process analyzer and instrumentation, and we serve a wide range of markets from environmental monitoring to oil and gas and hydrocarbon processing, things like refining and petrochemical, natural gas, power generation, and many others. Our engineering and manufacturing activities take place in several facilities in North America. We have one in Calgary, Canada, one in Pittsburgh, Pennsylvania, and one in Newark, Delaware. And we have direct sales offices and service offices around the world to support our customers, as well as a factory-trained set of manufacturing representatives and distributors as well. So with that, I will turn the presentation over to Tim and let him start. Tim, the session is yours.
Thank you, John. Well, good morning, good afternoon, good evening. Thanks for joining us today. Today we're talking specifically about flue gas analyzers for safe combustion of high hydrogen fuels. And the purpose of this webinar is to talk about the role that flue gas analyzers play and how they can drive safe combustion of high hydrogen fuels. We're going to talk about some of the trends driving decarbonization, some of the risks associated in differences between using hydrogen as a feedstock versus methane. We'll also talk about the three critical roles of flue gas analysis, different types of detectors that are used for measuring hydrogen, and then also the key flue gas measurements for combustion safety with hydrogen fuels. As John mentioned, feel free to write a message in the chat if you have any questions. I'll also be monitoring the chat while I speak as well. There'll also be time at the end for questions. So diving right in, let's talk about trends in decarbonization. So as you may be aware, there's a lot of hype and talk around reducing greenhouse emissions and really supporting climate control and supporting climate change. So governments internationally have talked about, what is their role in reducing greenhouse emissions, and there's been discussions on different initiatives across different countries, different companies, and different states, including the reduction of CO2 emissions. Now, there are many industries that will still require combustion for power and heat purposes. And this includes the hard to decarbonize industries such as steel, cement, and chemicals, as well as other forms of mobility like ships, air traffic, and even trucks and other types of ground transportation. So combustion will continue to be important, and there's thoughts of how do we think about the next generation of combustion. And finally, really large-scale decarbonization to decarbonize the whole industry has a lot of different paths, and there's paths around carbon capture to reduce emissions from the combustion process after the fact. There's electrification to generate heat in place of combustion, and there's also hydrogen fuels as a way to generate heat without carbon emissions. And so combustion will remain important in our future and in the move towards decarbonization. Now, if we talk about the large-scale decarbonization methods, I mentioned that there's carbon capture. Now, carbon capture is great from the standpoint of it directly removes the CO2 from the combustion process. It could be pre-combustion, post-combustion. And it's economical, especially for applications that are centralized, where the emission sources are in one place. Now, the challenge is when there are many point sources, when there's many dispersed sources, you have to think of a way to duct or to bring all of those respective stacks into one place. So very costly, and it's something to think about, especially for existing installations. There's also electrification to generate heat in place of combustion. Electrification is well suited for greenfield plants and low temperature applications. Becomes more of a challenge, though, when you have existing plants, and also the fact that you're dependent upon an external power supply. Now, it could be renewable for sure, but it's also how do you have that constant, reliable external power source for the heat of that process. And then finally, when it comes to evaluating hydrogen as a fuel, especially for existing plants, hydrogen fuel by itself, hydrogen reacts, does not form any carbon emissions, any CO2 emissions. By using hydrogen as a fuel, it's versatile for both centralized sources as well as small dispersed sources. It also has less impact for like most burners, because a lot of burners, maybe with a couple tweaks, can accept a hydrogen fuel. And also with considerations like that, there's no plot space for additional equipment to support a hydrogen fuel. I mean, you can just leverage existing utilities and existing plot space as it is without any changes for the burner or the fuel source itself. And then finally, hydrogen is used in a lot of processes right now as refinery fuel gas, as a byproduct of the fuel, as a byproduct of their industry themselves. So like there's refinery fuel gas where refiners use to offset some of the CO2 emissions in their own plants. And the important thing about that is it's already being generated, and it's already being generated up to like 76% hydrogen in some cases. So there's a lot of existing sources for hydrogen as a fuel source. So bring it all together, hydrogen really offers the most versatility for existing combustion processes. So let's talk about the physical properties of hydrogen and what makes it unique. And that'll help us really inform how we think about the risks and implications of using hydrogen as a fuel. So one thing, when we're thinking about physical properties, we can think about the molecular weight. Okay, so hydrogen is much smaller compared to methane. It's 8 times less mass. Hydrogen's also, as a result, 8 times less dense compared to methane. And because it's a small molecule, it's also comparatively faster. It's 3 times faster compared to methane, uniquely. So, and beyond that, because it's just a single bond, it's also additionally flammable. It's a much wider flammability limit from 4% by volume up to about 75% compared to methane, which is 5 to 15%. So when you look at just the physical properties of hydrogen versus methane, you start to see that hydrogen is 8 times lighter, it's 3 times faster, and it's more flammable compared to methane. Okay, those are important things to think about. Well, what else? Well, let's look at the actual combustion properties of hydrogen. Now, if you look at the heating value of hydrogen on a volumetric basis, you would technically need more volume. You would need 3 times more hydrogen to get the same heat release. So if you have a boiler operating at 10 million BTUs, you would need 3 times as much hydrogen by volume to be equivalent to the amount of methane heat release that you're providing with the methane flame. Okay, so 3 times higher volume would be needed to have the same equivalent to methane. But then if you look at it from a mass flow basis, you need roughly a third of the amount of hydrogen to equate to the same amount of heat release from a methane perspective. So when you talk about anything hydrogen fuels related, you really want to be sure of whether or not you're monitoring the flow rate on a mass flow rate or a volumetric flow rate basis, because they directly change how much much hydrogen is needed for that process. So be mindful of that. Other things to think about is flame speed. So because it's a small flame, it's a fast flame. It's also 10 times faster compared to methane. And that could be an issue of flashback, especially if you don't have enough air coming to a burner. If you don't have enough air coming to the burner at enough of a flow rate, you could have an instance where the hydrogen flame walks backwards in the burner, creating a flashback scenario. So that's something to be mindful as well, that it's a faster flame. Also, it's slightly hotter. The adiabatic flame temperature is slightly hotter compared to methane, so it's not a little bit of a surprise there. The auto ignition temperature is also a little bit lower, so it's a little bit less temperature is required to make it react. And then interestingly, but not surprisingly, the minimum ignition energy is 10 times less compared to methane. So if we think about like a spark, or like if we think about some type of ignition source, hydrogen needs 10 times less energy compared to methane on a millijoules basis. So when you look at it from a combustion property standpoint, hydrogen flames are 10 times faster, they burn hotter, and they have different heating values depending on whether you're looking at it from a volumetric or a mass flow rate basis. Okay, now some other things to keep in mind is also the implications on air supply. So if you look at the combustion reaction, hydrogen requires 20% less air compared to methane for the same heat release. So if you're looking to, if you adjust it for heat release, 3.1 moles of hydrogen versus 1 mole of methane, you're going to need 1.6 of oxygen comparatively, and as a result, you generate, you need less air compared to what methane is. So if you're switching between methane fuel and hydrogen fuels, you need time for the burner to get the additional air needed for methane. Otherwise, you have the risk of incomplete combustion because you didn't add enough air. You didn't supply enough air to the methane flame. So if you're switching fuels, something to be mindful of is that hydrogen needs less air, but you're going to need to add more air if you're going to switch back to methane at any point. There's also the potential for higher NOx emissions because hydrogen is a hotter flame, it's a faster flame, it's also a shorter flame, and shorter flames have more potential for hot spots, and those hot spots are what directly create the risk of higher NOx. So there's also potential of higher NOx emissions as well. So that's just an overview, just like how to think about hydrogen versus methane from a combustion property standpoint. If we look at some of the potential risks, though, the potential risks follow all of these physics and all these different properties. So we talked about before, there's the risk of flashback in a premix burner, especially because that faster flame speed could consume all of the oxygen more quickly, and if the air is not supplied fast enough, it could walk backwards and potentially create a flashback scenario. Something to think about there. The next thing is really the risk of more thermal NOx because the flame burns hotter, because it's a shorter flame and a faster flame. There is the potential for higher NOx emissions. And also because you're generating more water as a result of a hydrogen flame, that could technically impact a permit that's written on a ppm level basis compared to a mass flow basis. So want to be mindful of how does that affect your permit if it's written in a dry basis, because if you start subtracting out taking out the water from the basis of the permit, you're going to be showing more NOx comparatively. The next thing to think about is really is also like the risk of radiant tubes. This is really for certain types of geometries within the firebox, but higher temperatures, the radiant section could create a potential overheating event. So something to look for there, especially as the flame gets smaller and shorter. And in the same respect, there's also the risk of overheating near the burner, because if a smaller flame is existent, it's a smaller flame and a hotter flame that could make anything around the burner throat hotter. And if the metals are not designed for that type of temperatures, they could create an overheating event or some type of burner leak. Now, we talked a lot about just some of the risks for hydrogen firing, but what about flue gas analysis? Now, the risk of accumulation of a combustible vapor is really where there is really where flue gas analysis plays a critical role in increasing safety and also reducing risk by monitoring for some type of unsafe condition. Now, before I go too much into that, I do want to share just some thoughts around flue gas analysis in combustion. So if we just look at combustion by itself, any combustion process needs oxygen, fuel, and heat. And if you're going to have a high hydrogen fuel, which has a mixture of hydrocarbons and hydrogen, there's going to be some type of incomplete combustion in the form of what we call combustibles. And if you're using those combustibles in the form of carbon monoxide and hydrogen, unburned hydrogen, would be due to things like poor mixing at the burner. It could be from changing loads of the burner, switching fuels. It could be malfunctioning burners, like I said, with a burner tip fouling off, or overheating, or something like variable fuels. So we want to think about incomplete combustion and these ppm amounts of combustibles that are generated to monitor for incomplete combustion. There's also, as a result, some relevant combustion measurements. So there's the measurements of excess oxygen, which we'll talk about more to drive as a process set point for the combustion process. So just giving it a set point. We'll also talk about combustibles in more detail on burner optimization and also safety to save fuel. And we'll talk again about measuring the methane and hydrocarbons in fuel at the very beginning to detect flameout, and then also having a representative sample to make sure that you are monitoring the process correctly. So all that being said, let's dive into each of those. And when I think about flue gas analysis and with respect to combustion, I think about like the flue gas. I think about stoichiometric combustion. Okay, so stoichiometric combustion is in this instance where you have the perfect amount of fuel and oxygen. And in the case of perfect conditions of fuel and oxygen, you result in entirely CO2 and water, especially for like a high hydrogen fuel. If that were the case, you would generate CO2 and water and then have some type of nitrogen passing through. Now in stoichiometric conditions, you have the perfect amount and you have maximum efficiency. And also notice that you don't have any excess of oxygen. Now in the case of normal operation, most furnaces and heaters, they operate with a slight bit of excess oxygen, where there's a little bit of excess oxygen, a little bit of excess air at the burner, causing a little bit of excess oxygen in the flue gas. And when we think about this setup, it's about 6% less efficient to add a little bit extra excess air at the burner compared to at the than stoichiometric conditions, but it's also safer. And it's also safer. And I say safer because while you have an excess of air at the burner, you have an excess of oxygen in the flue gas, you also only have low ppm levels of carbon monoxide and hydrogen. So there's no astronomical amount of combustibles present. Now that's to be contrasted with like a dangerous scenario or a fuel-rich condition where you have too much fuel and not enough air. And in these cases where you have too much fuel and not enough air, you're less efficient, 35% less efficient comparatively, because not all of the fuel is combusted. It's not fully extracted. You have incomplete combustion in the form of very high levels of combustion or combustibles, and no excess of oxygen either. So in the previous case, we had an excess of oxygen in a fuel-rich condition. In the stoichiometric condition, we don't have any excess of oxygen. So I'm going a lot into combustion, but I want to make something a little bit more clear. So if we have hydrogen as a fuel, okay, well, we have to be mindful of what's a normal amount of hydrogen as combustible, or if we have high hydrogen fuels that have some amount of hydrocarbon too, we want to be mindful of what's a normal amount of combustibles versus a unsafe condition. So let's talk about just the correlation between excess air at the burner and the excess oxygen in the flue gas. So I actually did the math, like these graphs came from my own actual analysis. But what you see is if you say 3% oxygen, okay, so 3% oxygen in the flue gas from a flue gas analyzer, that correlates directly to about 20% excess air at the burner. So there's some amount of safety margin associated with that you have at the burner of extra combustion air at the burner. Well, what about like 2%? So 2% would roughly translate to about 12% excess air at the burner. And so for normal applications for most fired heaters, you operate right within this, between this 2 and 3% excess oxygen in the flue gas range, and that range correlates directly to about 11 to 20% excess air in the burner. Now, what happens if you have hydrogen? And this is something I wanted to make sure I looked into. And if you have hydrogen, the graph just looks a little bit slightly different. And that's interesting because there's still, one thing to point out, that there's still a correlation, and two, that the correlation is still pretty strong. So instead of it being about 11 to 20%, it's the same range is about 12 to 20% range at the burner. So if you're having a hydrogen fuel or hydrogen fuel mixture, your excess oxygen in the flue gas will still directly correlate to approximately 12 to 22% excess air at the burner in the form of combustion air. So, okay. Now, the importance of excess oxygen, I mean, fired heaters traditionally are operated with respect to monitoring the oxygen measurement, the oxygen flue gas measurement, and that flue gas measurement at the stacker, we would recommend outside the radiant section, that would directly drive or support the amount of control of air to the burners, so that there's enough air to meet the burners and to meet the amount of fuel that you have at the burners. So the excess oxygen measurement is important to control the secondary air to manage the air-to-fuel ratio at the burner. And then from a standpoint of excess oxygen in thermal oxidizers, I used to design thermal oxidizers. It was the same idea where you had your excess oxygen measurement driving the amount of secondary air to fully oxidize any of the waste contaminants in the stream. So it was also heavily used in thermal oxidizers as well. So we talked about the important role of operational set point. And when it comes to like the critical role of flue gas analysis, okay, well, any flue gas analyzer should provide a operational set point in the form of like an excess oxygen measurement. After all the combustibles are consumed, what is left over, that's the measurement made. And that measurement is directly correlated to the air-to-fuel ratio at the burner, just like all those charts showed. There's a direct correlation of 3% oxygen being about 20% air at the burner. And as a result, that provides a sufficient amount of air safety margin provided to the burner. So we talked about the operational set point, but what about optimization? So flue gas analyzers also play a role in optimization, whether they're hydrogen-fired heaters or whether they're high hydrogen-fired heaters. So the role of optimization is important because we talked about this. We talked about this graph where as you increase excess oxygen, you also increase the correlation of air at the burner. The thing is, that also has an increase in CO2 emissions. So as you go higher and higher, higher levels of excess oxygen also correlate directly to higher levels of CO2 and higher levels of NOx, because you have more and more air available to create a hotspot to create NOx. And as a result, as you use more oxygen, you also have higher fuel usage. So from an efficiency standpoint, it is important to think about, well, what's the excess oxygen? Because if it gets too high, you have some amount of additional unnecessary CO2 emissions and NOx emissions and fuel usage. When you go look at a combustibles measurement, so as you go monitor for that CO2 and hydrogen and ppm levels, as you reduce the level of excess oxygen, you also get higher and higher levels, gradually higher and higher levels of combustibles, and then it gets to some point, which we call combustibles breakthrough. And at that breakthrough point, it goes close to stoichiometric conditions. You start to see astronomical, like exponential increases in the combustible levels. So we want to be sure that we're not too close to the combustibles breakthrough point right here. So flue gas analyzers also provide that monitoring for this type of combustible breakthrough, making sure that you're not, if you have hydrocarbons in your fuel with the hydrogen, you want to make sure that you don't get too low. You can't detect this type of combustible breakthrough point. Okay. Well, if you put these two graphs together, and you have an excess oxygen measurement and a combustible measurement, you'll start to see that you have two reference points. And if you might have just an oxygen measurement by itself, maybe 2%, that 2% excess oxygen measurement is without any additional context. But if you have a combustible measurement, you can gradually lower the excess oxygen in the process without getting too close to that combustible breakthrough point. So a flue gas analyzer also provides an opportunity to optimize your process and provide an optimum control point, lowering both the CO2 and NOx emissions created, the fuel usage, but also avoiding unsafe conditions with a combustible breakthrough point. So again, excess oxygen by itself provides that set point, just a single set point. But if you have the additional reference of combustibles, you can monitor for efficiency, and you can reduce emissions from lowering fuel consumption and also avoid the combustible breakthrough point. Now, the one thing to point out is that combustibles vary by the fuel that you use. So that's both, so it's very dependent on the process. So if you have a hydrogen fuel, that could be very different than a high hydrogen fuel, which could be very different from natural gas. Now, this is a little bit extreme if you compare coal versus oil versus gas, but it's pretty, it's pretty clear how different they can be. Coal being a lot higher, between like 5 and 6% excess oxygen before it gets to breakthrough, versus like natural gas and oil, where you have lower amounts. So because you have variable fuels, because you have dynamic mixing, because there's different humidities and all these things, that's why there's no fixed value for all cases. And that's why we recommend having the optimum excess oxygen level with a combustible measurement, so that you can monitor it real time and make sure that you're not too low and not too high on your excess oxygen. So we talked about the role of a flue gas analyzer in providing a role of optimization and efficiency. And by monitoring the combustion process for combustibles, you have that additional reference point for optimum amount of air. And you also have the ability to reduce your CO2 emissions and NOx emissions by reducing the amount of fuel that goes into the system. Okay, well, what about the role of safety? Well, we talked about the combustible breakthrough point, and that's one element where the combustible measurement is important, because you want to make sure that you detect combustible breakthrough. So let's add that to the list. So ppm levels of combustibles to alert for incomplete combustion. There's also an instance of like a fuel leak, or in a case where like the flame goes out, or something like where the fuel is leaking from a burner, especially if you have multiple burners in a fired heater, and one of those burners goes out. How do you know where the flame out is? So with a hydrocarbon detector, you can alert for high levels of fuel, whether that's a high hydrogen fuel or a hydrogen pure fuel, and it'll allow you to detect. It'll allow you to detect when you have a very high flame out condition. And so that would be from flame out from a fuel leak, where like the burner tip may foul up, or in a case where combustion air is going too fast, or in the case of startup, where you have startup and light up conditions and you don't have enough purging. So in any of these cases, you can use a methane and hydrocarbon detector to alert for these types of loss of flame conditions. Okay, so that's really when it comes down to the role of safety. Flue gas analyzers also provide that extra assurance that you have um, not too much incomplete combustion and also no like loss of flame or fuel leaks, detecting those at percent levels. Okay, so we talked about fuel gas analysis, and that's just a lot to think about, sure. But let's talk about the measurements behind this. So if a flue gas analyzer provides an operational set point, a means for optimization, and a mechanism for safety, how can you measure hydrogen in the form of combustibles for incomplete combustion, and how can you measure it at percent levels? So that's where catalytic detectors come in to measure hydrogen. There are two different types of catalytic detectors that we use and recommend. There's the RTD type, which has two different RTD elements. One is the active and one's the reference. And then there's also, it's much more thermally stable, but it's a bigger element, but it provides a good mechanism for monitoring for combustibles. And then there's also the catalytic bead hot wire detector, which uses two little Pellister beads that also monitor for the ppm levels of hydrocarbons and of hydrogen. So those are the two different types of catalytic detectors. Both of them, I would say, are designed to monitor for combustibles, and we use both of them for combustibles. And as I mentioned before, in both of these cases, there's going to be a active element and a reference element, and that's what that allows you to compare the measurements and compare to monitor for combustibles and or hydrocarbons. Because they're catalytic, they do require the available oxygen in the flue gas to oxidize the sample. So if you start to run very low on oxygen, we actually have a failsafe that actually alerts for high combustibles and high methane when there's limited oxygen present, because we want to make sure that there's always enough oxygen present, and if not, that there's an alert for them. But that being the case, because they're catalytic, you need oxygen present for them to measure combustibles. Now, one important thing to think about with catalytic detectors is that they're a catalyst. So they're not speciated. They can really measure what I call a zone of reactivity. So in a very specific window of operation, it can monitor for combustibles like carbon monoxide and hydrogen. And our combustible detectors are calibrated for carbon monoxide and hydrogen. But if you wanted to measure for methane, you'd have to operate at a higher temperature, and that's a different zone of reactivity for measurement. So calibration really refines the measurement reading, and it provides what I call an umbrella measurement. So it's any of those compounds that are measured within that range of reactivity. So carbon monoxide to hydrogen and combustibles, that's one umbrella measurement. Hydrogen, hydrocarbons, methane, that's a different umbrella operating at a higher temperature, different reactive zone, if you will. So that's important to think about. And when we think about like measuring hydrocarbons and cracking methane, because methane is one of the hardest fuels to crack catalytically, we use a hot wire type detector for that to crack methane for hydrocarbon measurement readings. And then we also use a hot wire type detector for high sulfur cases in combustibles, for monitoring combustibles in very high sulfur cases. So different detector types are useful for different types of services. And then, as I mentioned before, these detectors are also tuned for different ranges of measurement. So combustible measurement is designed for 0 to 2000 ppm related range measurements for combustibles. A methane hydrocarbon detector is designed for 0 to 5% measurement readings and ranges. And one thing that we've definitely uncovered is that if you're using hydrogen as a fuel, or if you think hydrogen is present, it is important to to calibrate with some amount of hydrogen, because that allows the detectors to be more sensitive to hydrogen, to put it under the umbrella, and also to make sure that you get the proper responses for hydrogen, especially for hydrogen, percent hydrogen leaks. You want to make sure that you have some amount of hydrogen in that calibration gas so that you can monitor for more precise levels of hydrogen. Okay, so when it comes to combustion measurements, we talked a lot about the properties of hydrogen, what makes them. We talked about combustion, the basics of combustion. We talked about flue gas analysis and and what to think about flue gas analysis. Let's talk about the combustible measurements. Let's put it all together in one place. Well, if you're using high hydrogen fuels, it would be worthwhile to have an excess oxygen measurement for safe combustion control. Basically, having an excess oxygen measurement to make sure you have enough excess air at the burner, make sure you have that operational set point, and make sure that you're not too close to stoichiometric conditions. And if you have a high hydrogen fuel which has some amount of hydrocarbons, it's also important to monitor for combustibles for safety and efficiency, because that ppm level, because it can monitor for ppm levels amounts of hydrogen and carbon monoxide, and especially if there's a mixture of like refinery fuel gas, high hydrogen and other hydrocarbons. It's important to monitor for some amount of carbon monoxide through a combustible detector. And again, we talked about carbon monoxide breakthrough and combustible breakthrough. Combustible detector provides that measurement for safety monitoring, making sure you're not too low to that stoichiometric condition. And like I showed you before, that previous slide about optimization, you really have that optimization set point for the air to fuel ratio at the burner, making sure you don't have too much excess oxygen and then not too little, where you're getting close to a combustible breakthrough. And then also, it would be important to have a hydrocarbons detector as well, or hydrocarbon measurement as well, to make sure that you don't have a fuel leak, to monitor for safe light off during startup. And even in the case of like a tube leak, for example, if you were to have like a special type of if you have a type of process leak, a process tube leak, you could potentially detect that type of hydrocarbon as well. So for monitoring flue gas for monitoring flue gases with high hydrogen fuels, we'd recommend an excess oxygen measurement for combustion control, combustibles for safety and efficiency, and hydrocarbons for additional safety monitoring. Then when it comes to monitoring with pure hydrogen, where there's no amount of carbon monoxide present whatsoever, no amount of hydrocarbons present, you'd still monitor for safe, for excess oxygen for safe combustion control. That doesn't really change. You still need that set point to make sure you have enough excess air at the burner and enough excess oxygen in the flue gas for that set point. When it comes to monitoring for combustibles, there's still going to be some amount of ppm levels of hydrogen, even with its on ignition temperature, with its high reactivity, with its high flammability. It's very hard to get 100% oxidation of anything. And so it'd still be important to monitor for ppm levels of hydrogen, just to be sure that it's all fully consumed. So that also would provide a secondary point for air to fuel ratio, and potentially monitor combustible breakthrough, although you wouldn't really want to get to, you want to provide a higher safety margin at the burner to monitor, to not get too close to that the flammability, to not get too close to like a flammable mixture or some type of fuel-rich condition. So combustible measurement would also still be important for monitoring ppm levels of hydrogen. And then you could use a hydrocarbon detector, or a methane detector in our case, to monitor for percent levels of hydrogen. Again, I'd recommend calibrating more for hydrogen in that case, because it'd be better tuned for that hydrogen zone of reactivity. But again, if you're using hydrogen as a fuel, you could monitor for percent level hydrogen from like a burner fuel leak, or like some type of like safe light off condition, to make sure that you don't have any buildup of hydrogen in the firebox at a percent level basis. So those would be the flue gas measurements for pure hydrogen as a fuel. Okay, so we talked a lot about a lot of different things, and I'll kind of pull it all together as far as the takeaways are concerned. So we mentioned that hydrogen fuels are very versatile for solving the issue with how do you decarbonize existing combustion processes. especially with their small dispersed point sources. So hydrogen fuels are one way to very quickly convert burners from hydrocarbon fuels to hydrogen fuels. So that's one solution to decarbonization. But one thing to think about is, again, the properties. So hydrogen is 8 times lighter. It's faster diffusing. It's more flammable compared to methane. And also, hydrogen flames are 10 times faster. They burn hotter, and they have different heating values depending on whether or not it's a mass flow basis or a volumetric basis. So these are things to keep in mind when switching to a hydrogen fuel or offsetting or spiking hydrogen in your fuel source. Other things to think about, like I mentioned, are like the risk of flashback. So making sure that you, especially if you have a premix burner, making sure that you have accommodations to have enough combustion air at all times, especially if you're planning to switch from hydrogen to methane or something like that. Make sure that you can offset those types of swings, and also be mindful of the risks around higher NOx, especially if your permit is around a volumetric basis. And then finally, in a dry basis, for example. And then we also talked about the 3 critical rules of a flue gas analysis: the operational set point, optimization, and safety. Flue gas analyzer, when purchasing a flue gas analyzer or prescribing a flue gas analyzer, it'd be important to bear in mind what are you working to solve? Are you looking for an operational set point? Are you looking or are you looking for a optimization control set point? Or are you looking for safety monitoring? So those 3 critical rules are important when you think about a flue gas analyzer. And then when you look at the actual umbrella measurements behind them, catalytic detectors really provide that zone of reactivity for ppm monitoring of combustibles, and also percent levels of hydrocarbons and high hydrogen to ensure you have safety and with any type of high hydrogen fuel source. So with that, I thank you for your time. Feel free to put your message in the chat. I don't know, John, if you've seen any messages. I see a couple of questions in the chat.
Thanks, Tim. Yeah, there's a couple of discussions going on in the chat. Maybe the first one, I don't know if it's a question as much, Tim, but just maybe some comments. I don't know if you have any, but Richard commented that in the Canadian Electrical Code, the auto ignition temperature for hydrogen is a bit lower than, say, the other standards, and nitrogen is typically used as a diluent to stay within meteorological limits. So I don't know, metallurgic limits, excuse me. I don't know if you have any comments on that, Tim, or if you've seen any variances on standards globally that you might want to add to that. That was sort of an information comment in the chat.
Well, I think that's a fair point. I'm not very familiar with the specific metallurgical limits, but I think nitrogen diluting with nitrogen will do 2 things. It'll reduce NOx, surprisingly, because you have less oxygen available. I mean, it certainly will increase the amount of nitrogen present, but by adding in inert, you inherently cool the flame. So that is certainly one way to, especially if you're concerned about hotspots or like changing from like a hydrocarbon-based fuel to a hydrogen fuel. That is one way to cool the flame, as adding nitrogen as a diluting with nitrogen as an inert, and also to have less available oxygen present to drive the NOx formation. So I agree with it, but I'm not sure any other details other than that, John.
Okay, no, that's good. The other part of that chat had to do with using methane during startup and shutdown when hydrogen is used as a fuel for combustion. I didn't know if you had any other additional comments or if you've seen that in other applications that you've dealt with.
I think that is certainly the wise choice when it comes to startup, only because we talked about the high reactivity of hydrogen, very low spark ignition required. There's been a lot of talk in the industry of continuing with methane as a startup fuel, because you wouldn't want any excess amount of hydrogen to build up in the firebox, causing an unsafe condition, even more so than having a methane buildup. So yeah, there's talk within the industry around maintaining methane as a startup fuel. Certainly going from methane to hydrogen, the hydrogen would use 20% less combustion air. So there would be adjustments for the combustion air as you switch back. But I agree with that statement, and that's something I have heard for safety to light up without having any potential risks of, additional risk with using hydrogen as a fuel for startup.
Okay, and I don't see any other questions or, oh, sorry, one question just came in. Tim, what is the international or Canadian standard for environmental regulations concerning burners and thermal oxidizers?
So environmental regulations.
Maybe that's one we can get back to, Tim, if you want.
Yeah, that's something I'd investigate more. So when it comes to fired heaters, certainly there are API standards like the API 556 recommended practice. That's one I would recommend for fired heaters. When it comes to boilers and thermal oxidizers, I know I referenced NFPA 86 a number of times. When it comes to the environmental side of things, I think it's really country specific, but I'd have to get back to you on that one.
Okay.
Yeah,
And the
great
second
question.
and the second question in there is, which type of analyzers are recommended for emission monitoring, chromatography or UV vis absorbance analysis? This is more around emissions.
Yeah, so when it comes to emission monitoring, that's a whole, from my perspective, that's a whole different universe of like continuous emission monitoring. So I'll leave that to certainly my counterparts. I don't know if we can get Michael involved with that question either, but really when it comes to flue gas analysis, that's where I think zirconium oxide comes as a recommended choice for technology for monitoring for excess oxygen, and then these catalytic detectors, RTD type and hotwire B type and catalytic B type, are useful for monitoring combustibles as an umbrella measurement for hydrogen. When it comes to other types of continuous emission monitoring, I mean, zirconium oxide can be used for continuous monitoring of flue gas, So, but we can get back to online. But any other questions on that specifically, John?
No, nothing there, Tim, and I'll try to get that email and we'll get in touch with on those questions as follow-up. And I don't see anything else in the chat. The Q&A, there was a question on the presentation, which I'll take up afterwards.
And I see there's some notes about continuous emission monitoring around for NOx, SOx, and for combustibles. So for NOx and SOx, I know that we have our 9900 series that is capable of that, but I get back to you on that one because we have our other product manager that can help with those questions too.
Right, and that's what I'll have Michael reach out on that. Yep. And I don't see anything else there.
Okay.
So, okay, so I would like to thank everybody again for attending the session today.
Yeah, thank you for joining.
Discussion was interesting as well. And Tim, I'd like to thank you for taking the time and sharing your expertise and insights there. I did post some links to our products as well as local contacts if needed related to the presentation today. And as I mentioned, we are recording it and we will be posting it on our AMETEK Process Instruments YouTube page in the next 1 to 2 days. So please feel free to go there to review again. And again, thank you for your time today. And I hope everyone enjoys the rest of their day. Thank you. Bye-bye.
Thank you.